The video that you are going to watch has been prepared under the INUP I2I program. This India Nanoelectronics User Program, Idea to Innovation, has been funded by Ministry of Electronics and Information Technology. The main goal of this program is to prepare trained manpower in the area of semiconducting, electronics and nanotechnology. This program has different levels, and the level 1 is the awareness program, in which we ask the participants either to come here in the institute, or they can also participate in the program in a virtual mode. In this level 1 program, they are given lectures related with the different fabrication and characterization facility, so that they can get aware of about these facilities and how they are going to use it for their research work. In the level 2, there is a hands-on training program, which is mostly for 1 week to 2 week kind of program, in which the participants come here, stay in the institute and listen different lectures related with that theme of this program, and also participate in the different experimental work. In the level 3, which is a very interesting part of this program, they can write a project proposal related with their research work, and in that project proposal, some work they can do in their institute and some work they will do here using these high-end facility that we have here in IT Delhi. Once the project proposal get accepted, the students or the faculty member can come here and use this facility for their research work. And once they get a good result, they can publish a paper, and they need to acknowledge these facility and this program. The video that you are going to watch is a part of this program. This has been prepared with the idea that you can listen different lectures about the fabrication and characterization facility at your own pace. You can watch this at your own time and see how much it is going to be useful for your research. I would request you to share your views at the mail given below, and we would be very much interested to know how much you have liked this video, and if you have any comments, you can write to us. Thank you very much.
Now let us come to the microfabricated. So here, these are the examples of microfabricated devices. So fabrication of integrated circuits, as in microchips, and MEMS, micro electromechanical system. MEMS, where did you see MEMS in real life? So inkjet print head. There is a cantilever which disperses the ink which is flowing from the top and spreads over the paper. Then laser diode. Laser diode, it is microfabricated device because the laser is microfabricated here. Otherwise, the laser looks quite large in size. Then this TFT screens, OTFT or TFT screens that you use in your mobile phones, and microsensors like biosensors and nanosensors integrated into these devices. So basically, microfabrication process will involve 3 stages: cleaning, and then heating, and then processing. So cleaning involves those silicon wafers, glass wafers or other wafers, because you need ultra cleanliness environment, because even a dust. So any of you can see the dust coming or passing through this light. So these many dust particles are already present in this room. Now if you are making a device with a microchannel of say 10 micron geometry, these dusts are or can be seen by naked eye. So at least they are 25 to 50 micron in diameter. So obviously if any one dust falls onto your micro channel, it will block it and you will not get any result, no passage of any liquid or air through that kind of micro channel. So you need to work in a clean environment. So HEPA filters will suck the air from this room, or rather it will suck the dust from the environment and flow the clean air into this room. Whatever dust particles are generated by human activity or any aberration activities inside the room, they are also collected and then passed through the HEPA. So there is a recirculation with some fresh air input every hour. How many changes of air is happening inside the room is that determines what particle count should be inside the room. So generally there are different classes of clean rooms. So in the bottom there are two types of airflow pattern. This is turbulent airflow pattern and this is laminar airflow pattern. So two types of clean rooms can be made. So laminar airflow is more expensive, and generally if you see or you might have read about these nanometer processes for making, say, Intel microchip or Snapdragon microchip, less than 15 they have reached. 5 also they have reached. So in order to process 5 nanometer structures, you need class 1 room. That means 1 dust particle per cubic meter. That is the allowed quantity. So there is still chance that that dust particle will fall down on some device. So as a result, if you make 100 devices, 1 devices will be contaminated and that has to be discarded. So the discarded devices actually adds to the cost of the final chip. So if you are making 100 chips, 1 chip gets destroyed, so you add the cost of the destroyed chip into the rest of them. For general purpose, this turbulent air clean room can also work. For, if you are working in class 100 or class 10,000, or you are simply packaging any medical devices such as injection syringes, so there also you need this dust-free environment. So clean rooms are that important. So these are the classification of clean rooms. ISO 1 contains 10 particles per cubic foot of air, should have less than 10 particles of 0.1 micron diameter and less than 2 particles of 0.2 micron diameter. So that is the concept. So sorry, these many particles are there. So that is class 100. Class 1 is ISO 3. And room air, as per definition, will have 35 millions of dust particles per cubic foot. So this room air definition is as per European standard. When the air quality index in that particular room is 50. If air quality index is 250, that means it is a logarithmic scale. So you can estimate how many dust particles you are inhaling if you are in Delhi. So 35 million particles having 0.5 micron diameter. So that is the room air. So class 1 lakh is having these many particles, and these are countless. That is why it's blank. Means there are too many particles. And class 1000 is what NRF has. Nanoscale Research Facility has these many particles per cubic foot of air. And in order to make a 5 nanometer process, you have to at least make class 1. And at class 1 also you have so many particles. So within the class 1 also you have to take some extra precautions to remove that many dust particles also. So cleaning is most important, surface preparation and substrate cleaning. So growth is the second option, like silicon oxide generation from silicon nitride fabrication on top of it, then gold deposition for track formation, etc. And the details are like this. So typically we choose these wafers as a base for microfabrication. So bases can be single crystalline, polycrystalline or amorphous. Single crystalline substrates are silicon, quartz, gallium arsenide, silicon carbide, gallium arsenide, and then lithium niobate and sapphire, alumina. So these are the common substrate which are suitable for semiconductors. So semiconducting property should be there on the substrates if you are making a solid state device. Now in terms of microfluidic biosensor, that is not the requirement, because there you need to create different kind of structures. You need microchannel, micropump, microvalve, electrodes, optical sensing element such as OLED coupled with a photodiode or MEMS device, these kind of structures. So base material is mostly replaced in biochemical sensor based microfluidic devices as glass. So glass is the chosen substrate because it is cheap and easy to microfabricate on. But if you are dealing with solid state devices such as pen drive or OTFT display unit, then these semiconductor based substrates are needed. For example, in pen drive, so pen drive you store the charge in one capacitor, nano capacitor. So you have to, after storing the charge, you cannot just keep it open in the loop, in the circuit. It will discharge. So programmable resistor will hold the information to hold the discharge of that capacitor. So that 1 and 0 of that particular resistor. Understood? Okay. So silicon wafers are common, but for microfluidic devices for research purposes and for medical applications, etc., you need glass because it is much cheaper compared to the silicon. So the clean room based cleaning involves these processes. So please make a note of it. I'll also share the slides later on. So wet cleaning and dry cleaning, these are the two different ways of cleaning the wafers. So RCA1 is based on cleaning with ammonia peroxide mixture, which removes the organic contamination from the surface. For example, there is a silicon wafer and accidentally you have touched that with your finger. So what the thumb impression actually contains which kind of chemicals? What are the chemicals which you can transfer in your thumb impression? Dead cells, skin cells, then sweat. What are the constituents of sweat? Sodium. Sodium is the most potent contaminant for any semiconductor device. If you have sodium contamination on any of the surfaces, you have to get rid of it only by etching it with hydrofluoric acid. So obviously you cannot touch any silicon wafer by hand, but somehow if you do, you have to follow all these steps: RCA1 cleaning, followed by RCA2 cleaning, and then piranha cleaning, and then finally HF dip. So RCA cleaning removes organic contamination and RCA2 cleaning removes metallic impurities. So RCA1 is based on ammonia peroxide, it is corrosive oxidant, and RCA2 is hydrogen chloride HCl peroxide mixture. It removes the metallic impurities like lead, arsenic, or any other contamination which is there in the wafer surface. But sometimes you are purposefully doping some of the metal in the silicon crystal itself, and for making say NP junction, etc. So that dopant is also removed. The top layer of the surface will be absolutely clean from the metal impurities. That is one of the demerit, but it won't lose the so much of efficiency if it is a dopant is useful to you, because dopant will be present. If this is 500 micron level thick silicon wafer, there is still some thickness left after the surface cleaning. The surface cleaning will only take away few nanometer, 1 or 2 nanometer top surface. If you are dipping that in HF, it will take away say 100 nanometer or 200 nanometer or 1 micron top surface, but still you will be left with the rest of the wafer thickness, which is sufficient for you to get the semiconductor device made. Okay, piranha is the quick solution. Sulfuric acid peroxide solution is a quick solution, because once you clean the wafers with RCA1 and 2 and then hydrogen fluoride, you get a very pure wafer, surface cleaned wafer, and then you can store it for some times. But storage comes with another demerit, is that the silicon wafer slowly oxidizes in the natural environment. So you want silicon surface, but you are getting 1 nanometer thick silicon oxide on top surface, which is making a insulating layer. So which is not conducive for making a conductive layer on top of it. So you have to again either dip it in HF before use, or for quick cleaning you can also do piranha cleaning. So that will also remove the top impurities which has been gained during storage also. Type of deposition techniques. Now on silicon, if you want to grow silicon oxide, exactly, dielectric, if you are making a semiconductor, obviously you need an insulating component also. Insulator, non-insulator, non-insulator surfaces. And on top of conducting surface, you have to also make contact pads, these circuit elements, so which are typically made up of gold. Gold does not stick on the silicon surface. It will come out. So you have to deposit chrome or titanium first to say 10 nanometer thickness. That is an adhesion layer. On top of that, you have to deposit gold. Gold, silicon, silicon oxide. And if you are making cantilever, then silicon nitride. So these are the different processes that you have to follow anyways on each of the chips. Common processes can be classified into these four: oxides, etc., like OTFT, organic thin film transistor. So what is the ingredient of OTFT? Why does it emit color or light? A dye which can be excited under a particular voltage, that has to be deposited on a particular dimension to make 1 pixel. So that dye is the third party chemical that I am talking about. So deposition. So it comes under deposition process. Oxides can be created using oxidation process, and metal deposition can be done using physical vapor deposition or chemical vapor deposition process. So these are the 4 common steps in those solid state or microfluidic device fabrication. The 5th one comes with the micro channel when we talk about microfluidics. So that will have a different one more steps apart from these 4 which I talked about. So we'll come to that one by one. So the electronic devices that have this, which are conductors, metal, then insulators like dielectric and semiconductors. So the purpose of the thin films are these. Then optical devices need reflective surface, transparent surface, light guiding surfaces and scattering regions. And films may also have a chemical or mechanical purpose, such as for making MEMS devices, cantilevers. So silicon nitride will be required to make a cantilever. So while making cantilever, this is silicon substrate. On top of that, you grow an oxide, then you deposit silicon nitride and then etch out the silicon oxide so that silicon nitride will remain hanging as a cantilever. So that is the process. We will talk about that in the next slides. So techniques can be made using thermal oxidation, then chemical vapor deposition and physical vapor deposition such as sputtering and evaporative deposition. Thermal oxidation is typically involved with wet oxidation and dry oxidation. In wet oxidation, you pass vapor of water, pure cleaned water, over silicon. So silicon will be converted into silicon oxide and hydrogen. In dry oxidation, silicon is passed by plasma, oxygen plasma. So that oxygen plasma will corrode it and will convert into silicon oxide. So this is more expensive because you have to create a plasma. So plasma making device is more expensive. But vapor deposition, water vapor generating device is cheaper. But it is slow process and this is faster process. So cost versus time, that you have to optimize. For general purpose research, this is suitable. For large foundries creating mass production, dry oxidation is favored. So chemical vapor deposition, for example, if you want to deposit silicon nitride, which is not originally part of the silicon, then you have to follow CVD. Yes. Physical vapor deposition, there are 2 different types, sputtering and evaporative deposition. You will see that in the clean room, because that is what you came here for. Discussions won't solve anything, because you have already learnt it in the lectures and practicals. If you have any queries, you just write down the email and we will reply. But utilize that final session of 3 hours visiting the facility. Okay, unless you see the equipments, you won't be able to utilize it later. This is the chance. So CVD, PVD, you will see in the NRF, and there you ask the question to TA instead of learning from the slide. So oxidation, this is the furnace. Then chemical vapor deposition, again you will see that in the NRF. Physical vapor deposition, such as sputtering and thermal evaporation. So units are there in the our lab as well as NRF. You will see at site. But why I am showing these slides to you is that at least during the night you come across or you read about these techniques. Sputtering. How many of you are familiar with sputtering? So basically, ions are bombarded on a sputtering target made up of gold. Some atoms are released and the substrate is kept on the top. They will form a vapor like scattering and deposit on the surface. That is the principle. Now you have to block some areas of the substrate from getting this incoming metal ions. So you coat the surface of the wafer with a photoresist, a polymer, and then expose that with the UV. What happens? Wherever you have shown UV, the polymer will melt and it can be removed. For example, you want to make gold electrodes or track. So you will expose only those areas which will only form the track. Rest of the areas has to have different functions. So you will redo that by mask aligning. So wafers can be processed multiple times. In one step you are depositing gold, another step you are depositing something else, and so on. It is not a single step process that you can deposit and fabricate everything at once. They are layer by layer process of fabrication. UV has to be penetrating UV. That means it should be able to melt that polymer. Now the melting polymer is known as positive photoresist, and some polymers have quality after interaction with the UV, it does not melt, it solidifies there, crosslinks. So that is what you are going to do with the microchannel fabrication, SU8, negative photoresist. So for microfluidics, you require negative photoresist, and for patterning of gold and other features, you need positive photoresist. The target is bombarded with argon, and thereby it releases the metal fine particles, not exactly in the metal format, but fine particles, which gets deposited on the surface above. In thermal evaporator, the material is vaporized using high voltage supply, kilovolt of voltage, and the substrate is patterned and kept on top. How thick the deposition should be, you can monitor that using a crystal, because the crystal will also receive the same amount of vapor as the wafer. So the vibration of the quartz crystal is diminished when it receives some metal deposition. So patterning. So patterning can be done by photolithography. Shadow masking is out of question because nobody uses that anymore. Even for your own PhD research, you will not be doing shadow masking because they are macro structures. If you are fabricating, say, 10 mm by 10 mm across features, then you don't need UV photolithography setup. Just cut a stencil on aluminum film and then pattern it. That is called shadow masking. Photolithography with small features, micron level features, you need photolithography. Then etching. Etching is another technique which I spoke in terms of electromechanical device, this MEMS, electromechanical system, MEMS or cantilever. So you have to make silicon oxide layer, then deposit silicon nitride and then etch out the surface beneath it so that the cantilever can stay as a hanging layer. So etching is done by dry etching, which is plasma etching. But before you proceed with that, you have to protect the top layer. Silicon nitride should not get etched. So again you have to deposit polymer on top of it so that you can protect it. And then you dip this wafer by having one small opening somewhere through which the reactant or plasma or HF can go inside. So etching is performed in two directions. I'm coming to that next. Yeah. Okay. So in etching, typically, I'll tell you how the etching can be done. Yeah. Etching is not a vertical process. So etching creates a kind of V structure. So the direction of the etching depends on the timing. So more time you spend, it can reverse in this direction to create a cantilever structure. So if the time of incubation with the HF and your substrate is say 30 seconds, it will create a V valley. Then so slowly the surface will keep corroding and it will go and penetrate inside also to make the cantilever on both sides. And it will also go down toward the silicon also. So some of the silicon will also get corroded. So you have to optimize the conditions so that you get the cantilever but not lose too much of silicon. So that optimization has to be done at every process. So it is not that one process developed by someone will suit your need also. You have to generate your own process optimization. Alright. So patterning like silicon, then silicon oxide, then deposition of photoresist, and then UV irradiation through a photomask, which I just talked about. So these are the processes. So what structures can be created from this is this. So silicon oxide can be patterned, and this is so this photoresist is patterned, creating silicon oxide as exposed layer. Then you add etchant. So it can etch. Can you see a small cantilever structure here? So that is how it is etched. And then you remove the polymer from the top, you will get silicon oxide with the etched silicon oxide in this form. So recap, RCA cleaning, then microfabrication using mask. Photo mask should have a hole or gap through which the UV can penetrate down. How you can achieve that? Black ink. You take a transparency sheet, you coat that with black ink using any of the printer and pattern it in such a way that the transparent layer should penetrate the UV light and the black areas do not allow passage of light. That is how you pattern. When you pattern using this process, I told you there are two types of photoresist polymers. One is positive photoresist and one is negative photoresist. So the concept of positive photoresist is that upon exposure to UV, it melts or degrades, which you can remove, creating an opening like this. Instead, negative photoresist has a property that it will solidify at the surface where it has been exposed. So now a negative photoresist on a substrate is created like this, which looks like a pillar. Now if you pour this, if you keep this substrate in a petri dish, there is a silicon wafer which has been formed along with this negative photoresist. So negative photoresist has a pillar formed by UV exposure. So your silicon wafer, let's say you imagine a flat surface, for example your mobile phone screen, and imagine an elevated structure on top of it. You keep this mobile phone surface into a petri dish and pour flexible polymer on top of it, PDMS. Once PDMS is solidified, it is a flexible material. Then you remove your mobile phone and separate the PDMS from it. So what you expect from there? Mold, creating the same structure as your mobile display with some dip which is proportional to the height of this negative photoresist. And when you bond that groove onto another surface, glass surface, you will create a microchannel. So microchannel underneath the polymer PDMS surface, and the base material will be glass. So that is how the channels are created. So to make microfluidic structure, you need negative photoresist like this, and the glass which I am talking about should have the electrodes. That electrodes are formed using positive photoresist. So it is a two-step process. One step will not yield you both the top layer and bottom layer. Bottom layer is created by using another photolithography process, and top layer by using negative molding method. This SU8 pattern is negative molding because you are creating a groove. So examples of photoresist are SU8 for negative and AZ1512 for positive. To create this polymer coating on the surface, you require a spin coater, which you will see in the laboratory, because you need uniform thickness of this polymer. How much thick this photoresist layer should be will depend on what thickness you have deposited the polymer coating. So speed of the spin coater will decide the thickness. The higher the speed of the photoresist, it will form thin film. These are some examples, and these are the how mask aligner can be used for UV patterning, because the UV bulb which I talked about is a general illustration, but for precise alignment and removing the optical aberrations like ghosting effects, etc., you need a mask aligner, which are very expensive, because these optical corrections has to be very precise. The lowest size of the feature size you want to get, you need higher capacity mask aligner, which is much more expensive. To remove these things, very precise alignments are required. And if it is a multi-step processes, the alignment of the wafer exactly at the same location is very crucial, because once you have made the pattern at one particular alignment, you remove the mask, you remove the substrate for cleaning and other purposes, and realign that. How is it possible? You have to create some mark on the substrate itself so that you can realign it next with the photomask. So etching, I told you. Cantilever structure, how it can be created, I told you. Some videos on microfabrication you watch yourself. So microfabrication, like this macro electrode which you had seen in the yesterday's lecture, can be turned into this 1 centimeter by 1 centimeter size and the cantilever of 75 micron sizes. So that is the purpose of microfabrication, and you can create multiple units on the same wafer, and the advantage is array operation or multiplexing. So that will conclude today's lecture.